Hello, and welcome to Chapter 5, Section 1. So in this chapter, we are going back to something that we talked about in a previous chapter, these normal curves. Their official name is normal distribution. It's when you're, like, whatever graph you make, a histogram or something like that, if we kind of went over the outline of it, it would make that kind of bell-shaped curve. That's what a normal curve is. In this bell-shaped curve, there's a few properties that I want to talk about. So the first thing is that the mean, median, and the mode are actually all the same number when we're talking about a normal distribution. So a normal curve like this, the mode is usually where it's like the tallest point, but the median, because it's symmetric, is going to be right in the middle as well. And then the average, the mean, is also going to be right in the middle because it's symmetric. So our first two properties, the mean is the same as the median is the same as the mode, and our shape of this distribution is going to be bell-shaped and symmetric. Okay, so then the third property is that on both sides, the ends of the curve here, there actually is no end. They actually keep going on forever. We just don't draw it out like that because who has that time? So theoretically, they go on forever in both directions. This fourth property is probably going to be the most important for us because when we first looked at normal curves, this was when we were doing the empirical rule. There were these percentages with the 68%, the 95%, the 99.7% rules. And so the main thing here is if we were to shade the entire normal curve and everything under it, then the area, the total area, is 1. Or if you want to think about it as like 100% of it is colored in or shaded in. But the total area is 1. And this is important because basically for all of our normal curves, what we're trying to use this for is to calculate probabilities. Probabilities or like the area under the curve. So we're looking for percents, we're looking for decimals if you choose decimals instead of percentages. The last property is that we're going to be using standard deviations to calculate the distance from the mean. So we're basically saying like, oh, we're this far from the mean, this many standard deviations. So it's kind of like our unit of measurement here. And you might remember this because back in the day when we first did normal curves with the empirical rule, we would draw a line down the middle of the normal curve and we would label that with our mean. Then we would draw our 3 lines to the left and to the right of it to measure out how many different standard deviations we are away from the mean. So we're still doing those things, just we're going to simplify this process a little bit because in the past with our empirical rule, we could only find the areas when they were exactly on those lines, the numbers that we were looking for. And so now it's kind of like whatever number is fine. It doesn't matter whether they're on those lines or not. So an example of this is if the distribution of heights of all seniors in high school is normally distributed, so once you see those words normally distributed, you should be drawing a normal curve. So we're going to do that here. They told us it's normally distributed, so I'm going to draw that normal curve. They say it has a mean of 64 inches, so they're saying the average of the heights of these seniors is 64 inches. Which is not that bad. That's like 5'4". That's how tall I am. I'm average. And a standard deviation of 3 inches. So in the past, what we would do is draw our 3 lines to the sides and keep adding and subtracting by the standard deviation of 3. So here, we're actually going to simplify this process a little bit. We're not going to draw those lines anymore because we don't care as much about those exact lines anymore. I'm just going to draw a line, like a horizontal line from the mean, to show people like this is the standard deviation of 3. But when we actually do our calculations now, we don't need all the rest of the lines drawn in anymore. So that's kind of cool. Okay, before we move on into our calculations then, we need to talk about our standard normal distributions. So the word standard here means that no matter what the situation is, whatever the problem saying, whatever the mean is, because you know the mean they can give you any number for. Same thing with the standard deviation. Whatever the numbers they give you, we're going to use the same method to calculate our areas or our probabilities. So when we standardize something, we're actually using our z-scores. And so this was also something that we've talked about before. So if you remember, your z-score formula was z equals x minus the mean divided by the standard deviation. And so like if they give you the mean and the standard deviation every time, and then you would be able to plug that into our formula here. X is always the number that they're asking about in the problem. So that way you can figure out your z-score. Okay, so our z-scores are basically our standardized normal distribution numbers here. So our properties here are going to be pretty similar. Let's say z equals 0. So if the z-score is 0, that means on top, when we subtracted the x minus the mean, they would have had to be the same number in order for you to get 0 as your final z-score. So if they are the same number, that means on our normal curve, whatever the mean is, the x value is also the same number. So if we're finding the area to the left, where the z-score is 0, that means we're shading like halfway and everything to the left of that. Well, the area under the curve then is going to be half, because half the curve is shaded. So we can say this would be 0.5 as the area, or we can say 50% is the area. You can also think about this as a probability. So 50% chance that our z-score is going to be 0. Okay, if we're talking about a z-score of negative 3.5. So negative 3.5 on a normal curve, if we were to draw this out, because we know a z-score of 0 is going to be right in the middle, then negative 3.5 is, back in the day when we used to like draw this out with the lines, 1, 2, 3, 3.5 is like way out here already. So if we're shading to the left from here, something that's really far out to the left, that area is going to be really, really small because it's like so close to the end of the graph, even though, keep in mind, like that over here, that side of the curve technically goes on forever, but it's like a very small area that's actually under it. So when the z-score is negative 3.5 or even smaller than that, the area to the left is going to be about 0. Because there's so little area that's actually colored in, that's shaded in. So anything smaller than negative 3.5 is going to have an area of 0. Then on the flip side, if we talk about the z-score of positive 3.5, positive 3.5 is going to be on the right side of the 0, all the way over here. So again, if I shade to the left of this, now because 3.5 is like so far to the right, when I shade to the left of it to find the area on the left, now I'm pretty much shading the entire normal curve. So the area to the left is going to be about 1. Or if you want to think about it as 100%. With 0, it would have been 0%. I just didn't write it down. But anyways, so area to the left of a z-score of 3.5 or greater, even greater than 3.5, that area is going to be about 1, because anything to the greater than 3.5 would have been even more to the right, and so shading to the left is going to be about 1. Which also means that if you're talking about the area to the right of positive 3.5, to the right of positive 3.5 means there's like barely anything shaded, because now we're looking at this side, so that would be 0% again. So basically, as your z-score increases, that cumulative area underneath the curve, that shaded area to the left, also increases. So the bigger z-score you have, the area to the left is also going to be bigger. So here's where we get into the nitty-gritty of this section. So what we want to do with all these normal curves is actually to find the area under the curve. There's 3 different situations that you're going to have to deal with. The easiest one is finding areas to the left. So we've been talking about areas to the left up until now because we keep shading to the left. And so that'll be what's going to be the easiest and the least amount of steps. But we'll talk about the 2 other situations, and I'll teach you how to find all the areas. So first, we want to be able to find the area to the left of z equals negative 0.99. So anytime they're telling you a z-score, we're going to first draw out our normal curve, because z-scores always deal with normal curves. When we're dealing with z-scores, the mean is always going to be 0, like we talked about with the first property of a standard normal distribution right here. So 0 is in the middle. The standard deviation is always 1 whenever we deal with z-scores. Okay, so now that I have everything labeled, z-score of negative 0.99 means I'm going to be on the left side of 0. So, because it's a negative number. So it'll be about like here. And when you draw it out, it doesn't have to be like super exact or anything. We just want to make sure we label. So z-score of negative 0.99. And we are looking for the area to the left of it. So I'm just going to shade to the left really quick, just so visually I know what I'm looking for. And this will come in handy when we do the other two situations, when we shade to the right or in between. So just get into that habit of drawing it out, shading. Okay, so from here, with a z-score, before we had those like set percentages when we talked about the empirical rule, the 68%, 99% or 99.7%, the 95%. Here we don't have those specific standard deviations anymore. So when we deal with z-scores, we need another tool to help us find those probabilities or those areas. And this tool is called Table A. So you'll see it in your the notes assignment page on Canvas. I attached the document so that you can print it out. This is not something that you have to memorize, because look at it, it's like insane. There's so many numbers. So definitely not expected to memorize this. This is something you want to have convenient to you, maybe like print it out so that you can refer to it, or like bookmark it in your computer or something so it's easy for you to get to. Because we will be using this table for the rest of the year. So, to use this table, there's two sides to this. So on my left side over here, I have it so that all my z-scores are in this left side column right here, where it's labeled z on top. And then if you look at the other table, it also has the z-scores in that first column. Okay, but you'll notice that one side is all negative numbers, the other side is all positive numbers. That's kind of cool. Okay, so our z-score is negative 0.99. If you look at our z-scores here, they only have one decimal place. So to use this table, we use this first column to see what our first decimal place is, and then we use these rows up here to look for our second decimal place. So our first decimal place, with a z-score of negative 0.99, we are looking for a first decimal place of negative 0.9. So then on my table, I'm on the negative side. Negative 0.9 is right here. And so if you look at all this entire row of numbers, then all of these have to deal with the first decimal place of negative 0.9. But our second decimal place was also a 9. So negative 0.99, I'm going to kind of crisscross this so that I end up with this decimal right here, 0.1611. So by using this table, this decimal that they give me right here is going to be the area to the left of the curve. And if you look at this picture at the top, they're basically telling you, like, this is the probability, it's always going to be to the left. So all of the numbers in this table are always talking about areas to the left, and that's why it's easiest to find areas to the left. So we're basically saying this shaded area right here is going to be 0.1611 as a decimal, or if you want to think about it as a percent, 16.11%. Remember, to turn decimals into percents, you just move the decimal place to the right 2 times. Okay, so the reason why I keep saying area to the left is the easier one to find is because the table, once you find that number, that's your answer. Now I want to talk about areas to the right. So there's an extra step here because we're talking about areas to the right instead of to the left. So this time I'm going to find the area to the right of z equals 0.99. So this is a positive number this time. So if I draw it out, 0 is still in the middle because we're talking about z-scores with a standard deviation of 1. And then positive 0.99 would be somewhere to the right of 0. And we are shading to the right. So from 0.99 over to the right, everything over here. So we're looking for that area this time. So I'm still going to use the z-score table, but this time my z-score is a positive 0.99. So I'm going to make sure I use the positive side now. So remember that first column where you look at the z-scores, one side is positive, the other side is negative. So that's how you're going to decide which side to use. So 0.99, the first decimal place would be 0.9. Second decimal place is also a 9. So crisscross them, I'm going to end up right here with this 0.8389. So remember though, that table always tells you the area to the left. So that 0.8389 number we just found is only the area to the left. So basically what I found is if I had shaded over here instead, all of that area over there is about 83.89%, which makes sense because if I looked at what's over to the left, I should have shaded more than 50% of my normal curve because this is a much bigger area than what's to the right. And so if you're ever like, I'm not sure if I need to do an extra step or anything like that, look to see if the number you got doesn't make sense based on your picture, and which is also a reason why I like having you draw this picture first, because visually it's a little bit easier to check if your answer is correct. So here, the area to the left is 0.8389, or if you want to think about it as 83.89%, cool. But because we want the area on the other side, we basically need to do like the opposite, because if the area to the left is 0.8389, then the area to the right can be found by doing 100% minus what's on the left. So 100% minus the 83.89% that we got to the left will give me, if you want it as a decimal, 0.1611 or 16.11%. Okay, which is interesting because we got the same number as what we did before. Really weird. Because if you think about this, remember your normal curve is symmetric on the two sides. So a z-score of negative 0.99 versus a z-score of positive 0.99 means you're the same distance away from the middle. Just one's on the left, one's on the right. So when we talk about the area on the left or on the right, it's going to be the same amount on each side. So that's why our percentages were exactly the same. All right, so to summarize, anytime we're finding areas to the right, you're always going to have to do this extra step of subtracting the area to the left from 100%, or if you do 1 minus 0.8389, that would have gotten you the decimal version. Okay, the last situation I want to talk about is areas in between. So here, when we talk about in between, they're going to give us two different z-scores. Oh gosh, so let me draw this out first. If I draw my normal curve, the middle is still 0, standard deviation is 1. So we're looking for the area in between a z-score of negative 1.55, or negative 1.5, which means I'm over here somewhere on the left because it's a negative number. And then the other z-score is z equals 1.25, so that's positive somewhere over here. And we're looking for this middle section. Okay, to find that middle area, what we're going to do is, because our table only tells us areas to the left, if I find the area to the left of 1.25, because that was my second number, and then subtract the area to the left of negative 1.5, that'll give me that middle area. So it's kind of weird to think about. I like to think about it as like if I take the bigger area, subtract the smaller area, that'll give me what's in the middle. Okay, so either way, I tried to do it visually as well. This is what we're trying to do. So I'm going to start off by finding the area to the left of 1.25 as my z-score. So this is a positive number. When I go down to my tables, I need to make sure I'm on the positive side. So positive 1.25 means my first decimal place is going to be 1.2. So right here. And then the second decimal place, 1.25, is going to be the 5. So crisscrossing these, I end up with 0.8944. Okay. Then I'm going to find the area to the left of a z-score of negative 1.5. So this time I'm on the negative table, because negative 1.5. Negative 1.5 only has one decimal place, so that means my second decimal place is technically a 0. So negative 1.50 will get me the area of 0.0668 to the left. All right, so I have found the area to the left of 1.25. Then I found the area to the left of negative 1.5. So subtracting these two numbers together will find me the area that's in the middle, in between. So subtracting 0.8944 minus 0.0668 gets me 0.8276. Or if you want to think about that as a percent, this would be 82.76%. Which kind of makes sense because if we look at what's in the middle, this is kind of a bigger area. So yeah, the 82% makes sense. All right, so from the easiest to the hardest situations, areas to the left, just look at the table for the z-score. Areas to the right, find the number in the table for that z-score, but then subtract it from 1 or subtract it from 100%. Areas in between, find the two areas to the left and just subtract them. So those are the 3 situations that you'll need to know how to find. All right, thanks for watching. See you next time in next section's video. Bye.